Okay. So I think I will say something about relative quasimaps. So first, the definition. Um, so the initial definition of this comes from the paper by Chilken, Fontani, and Kim Malik. And but in their paper, they use slightly different names for these moduli spaces, and so in their notation, this should be called quasimap from a parameterized P1. To this black variety with the marked point at infinity. So the point is that on the one hand, you want this infinity to evaluate to a stable point. On the other hand, you also want this space to be proper. And the way you do that is when some singular points approach infinity, you let the curve bubble up so that infinity will avoid those singular points. So the um, the definition of relative quasimap, which I will call QMREL, consists of the following data. Um, so so first, our domain curve C will be either P1 or a chain of P1. And this comes together with a map phi from C to P1, which is isomorphism on the leftmost P1 and contracts all others. And you also need to keep track of this marked point infinity, a marked point. On the rightmost P1. And so pictorially, I usually draw it this way. So this is a parameterized P1. And then it bubble up to become a nodal curve of a chain of P1. And there's an infinity on the rightmost one. And so it's a quasimap. So it contains the information of a map from this C to the stack quotient, with the condition that the nodes and the infinity map to stable points. And we need one more condition, that the degree on each bubble is not 0. And yeah, and I should say the So this P1, I'll call it parameterized P1. And these other things that being contracted, I'll call it bubbles. And so from the definition, you can see they play a different role. So if I have two quasimaps, so they are isomorphic if there's a map between them, so that all the data are compatible. So you have C1, C2, and you have two projections. So in other words, for each P1 in the bubble, there's a C star worth of freedom that you can, if you change your map by an automorphism, that's considered the same map. But for this parameterized P1, if you multiply it by an element in C star, that's considered a different map. And of course, you can see that the non-singular quasimaps we discussed earlier is an open subset inside relative quasimaps. Are there any questions about this definition? Yeah, right. Like just the ones without bubble. And so of course the same torus we still have this torus action on the relative quasimaps. And we can, as before, we can fix an evaluation at infinity and talk about quasimap where infinity maps to some given point. So now we are going to do the same construction as before. So remember we have these correspondences, and one thing to notice is that when we do this correspondences, we are modify the quasimap at 0 in P1, and when we are consider relative quasimaps, we are bubbling up at infinity. Is there a question? What is the point of the map? How's it related to that? The point is, so this phi is used to parameterize this P1. So I should write this. So so here what I'm defining for you are closed points in this moduli space. But it's a moduli problem, so you need to say when are two quasimaps considered isomorphic. And the point of this phi is just to say that if this P1 is changed by an automorphism, that's considered different quasimaps. Yeah, that's right. So this is just to make it compatible with our construction earlier, where like we are implicitly considering the P1 to be a parameterized P1. So you can define these correspondences in the same way. Where you have two projection maps to relative quasimap of degree d and the relative quasimap of degree d plus delta I. So the EI and the FI, you can define them the same as before. But when you try to commute their commutator, which will define HI, so you realize that here we are defining it as an explicit polynomial, but this polynomial it will depend on this evaluation point, which in the case of relative quasimap, it is determined by the evaluation of the first node. So so this node for fixed point, it could be any W acting on x0. And this HI, you need to write it in a universal way. And the way to do it here, you can write it as tautological bundles, which is C1 Fi minus 1, C1 Fi plus I times epsilon, where the Fi is the pullback of the tautological bundle Vi at 0, where 0 is the point on your P1. Yeah, I'm yeah, it's I'm skipping one step here. So you have relative quasimaps, and you have the universal curve over this relative quasimap, and so this I'm writing a curly C. So it has a projection to the quasimap, and it has two sections given by 0 and given by infinity. The tautological bundle Vi lives over here. So you have this V1 to Vn minus 1 on this curve, and you pull back to the relative quasimaps. So, sorry. Yeah. It's supposed to be like a curly F. Yeah. Okay. Yeah. It's yeah. It's some sheaf on the moduli space. And one thing. So the first result in the paper is that this EI, FI, and HI forms an action of the involving algebra of GLN. And this is fairly straightforward. You can just check out fixed points, and it reduces to the calculation for non-singular quasimaps. But after this, there's another step that you need to describe the structure of this equivalent cohomology. I guess the question is how to describe this thing as a GLN module. So there are two things you can do. So either you take this whole thing and try to compute its graded dimensions and say like how many Verma modules there are in it. But there's another thing which I guess fits better into our initial goal to describe an indecomposable tuning modules inside this module. So the first thing to notice is that the dimension of this thing is very large, coming from some quasimaps which are kind of constant on the bubble, but they have some points that maps to the unstable locus. So I think this goes back to our earlier discussion of what do we actually mean when we specialize the Heist weight. So now let's say we fix lambda, which is a bunch of integers. Let's say we fix them to be in the decreasing order. And now we consider this module with Heist weight specialized to lambda 1 up to lambda n. And the specialization is by AI goes to lambda I times epsilon. And so this module as a vector space. Lambda I can be any real number. Oh, sorry. In principle, it could be anything, but the interesting case is lambda I are integers. So you can always do that. And the special thing about integer lambda is that the module you get, they will have non-trivial extensions between them. If the lambda I, they are all generic, you just get a bunch of Verma modules. Yeah, if they're generic, no extension. Yeah. So so this thing, you can, as a vector space, you can identify it with the usual cohomology of the C star fixed points of this space. Where this C star lambda is determined by it's the C star lambda. It's a subtorus of T determined by lambda I. And inside this space, when you take fixed locus, you can further decompose it into two parts, which I'll call M0 and M1. Where M0 are the connected components that intersect with non-singular quasimaps. And so usually the way I think about these spaces is that you have some larger space which is proper, and it has an open subset non-singular quasimaps. And when you take the T fixed points, so we know that non-singular quasimaps has isolated T fixed points, and the relative quasimaps, they might have isolated points, might have some connected components. So these are T fixed. So when you specialize to this C star, you have smaller actions, so you have bigger fixed locus. So some fixed locus, they might grow in a non-proper direction. So when you compactify them in this M0, you will add in something that's from relative quasimaps.
Even for generic lambda, you get this big fixed loci?
Yeah, for generic lambda, you will you will get the same fixed loci as T. So it's and this M0 is really just the fixed point inside non-singular quasimap. So so now we get a module which I will call H lambda W, which is just the cohomology of this M0. So first it depends on lambda because that's how we construct it, and it depends on W, which is implicit in this evaluation, and the second theorem about this is that this module is a direct summand of the relative quasimaps of this thing. Maybe I will call. And so using the stratification that I mentioned earlier, you can prove that this h lambda w it has I'll just say so it is a tilting module, but not in the usual sense. In what's usually called category O prime, where the reason for the meaning for this O prime is about the action of the Cartan element. So this means the modules where the action of the Cartan element is not semi-simple, but the action of center is semi-simple. And this module is known to be dual to the usual category O for regular high splits. And it turns out that this space they behave much nicer. You can actually compute their graded dimension, and you can see that the multiplicity of Verma module inside this module, I guess u lambda minus rho. This is given by the number of Bruhat paths from W to U. So in other words, there's a very explicit description of the fixed points, and you can just count how many points there are in each graded dimension. So far this sounds very abstract, but I'll do an example of n equal to 2. But before that, are there any questions about this part? Yeah, exactly. Like you can show that any t fixed point in M0 it's given by so first you have this parameterized component, and then each bubble must cover an invariant curve in the flag variety, and it must be a certain direction that you go from the smaller one to the bigger one. Yeah, that's why this Bruhat path appears. Like each P1 in the bubble covers invariant P1 in the flag variety. Yes. The green lines are the C star lambda fixed points. So T is a bigger torus, C star is a smaller torus. So you have less T fixed points and more C star fixed points. Yeah. Oh yeah, C star fixed points. Yes. So in general, this thing could be very complicated, but for n equal to 2, the things become very simple. So first, if we look at this non-singular quasimaps of degree d, and in this case, d is just one integer. This is isomorphic to c to the power 2d. And the correspondences is also isomorphic to c to the 2d. It maps to degree d, and it's an isomorphism. It maps to degree d plus 1, and it's a closed embedding. So first, if you do the construction for non-singular quasimaps, what you see is that for each d, it's a one-dimensional vector space. And this is the usual picture that you will see for SL2, where the map E goes this way. And the map F goes this way. So if you do this calculation of pull back and push forward, you see that F always acts by 1. And E acts by D times epsilon and A2 minus A1 plus D epsilon. And also here you can see it's a dual Verma module, because if you have A2 minus, if you specialize your parameter so that A2 minus A1 is plus some K times epsilon equal to 0, then this module will truncate at degree K, which means that there's a submodule from degree 0 to degree K minus 1. And what happens for relative quasimaps? I should say that this space M0, that I defined earlier. So an equivalent way of defining it is to say we take non-singular quasimaps. And take the C star lambda fixed locus and take their closure. So this is closure inside the relative quasimaps. And for this example of n equal to 2, if we choose lambda so that lambda 2 minus lambda 1 maybe plus k equal to 0, then the C star fixed points there are only two possibilities. Either is a point either is a point when the degree d is smaller than k, or it becomes C, a complex line, when the degree is greater or equal to k. And what will happen when you compactify these spaces? So the point doesn't change. And the C will compactify to a projective space, a weighted projective space, P1K. So so if you if you draw the spaces, it started as a point, but at some point it becomes a weighted projective space from degree k. Yeah, you can either find Verma or you find dual Verma. I guess in this case the Verma module is easier to see because for projective space the generators are the point class and the class for the whole P1. And if you take the point classes that forms a Verma, and if you quotient out by this Verma, the other the class is P1, they will form another Verma. And yeah, and I guess for n equal to 2, this is the good case that we actually get the indecomposable tilting modules. And when we'll get to bigger n, you'll find that the module constructed this way is it has dimension bigger than indecomposable tilting module. And yeah, I think it's still an open question of how to get the indecomposable one. And yeah, that's all I want to say today.
If these vertex functions have integral representation, do you try to use that to understand the question?
Not yet, but yeah, I was hoping that something can be done in this way. Yeah. Oh yeah. That's a good question. So I think that's another setting that you can that you can explore. That so the naive thing you can do is let's say from it's still a quasimap from P1, and so you see now you can not only twist at 0, but you can twist you can modify this quasimap at any point. So earlier we cannot modify at infinity because you want infinity to be non-singular, and now it's like if so 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 one thing you can do is you get a GLN times GLN action, and so in this direction you can do more crazy things, that you change your domain curve to be some higher genus curve, not P1. So you can still get some algebra action, which is expected to be U of GLN times the cohomology of this curve, which you probably, so when Okonkov was here giving a talk, you probably have seen something like this.
A couple of talks ago, I don't think he did
Yeah. I think something like this, or like some generalization of this, was used in his paper with Kasten and to identify some module that arise in their setting.